Hi everyone. So last time we've talked about the how to solve problems using uniform series compound interest formulas. So today we are going to continue to talk about it, and also we're going to talk about the uniform series. We're going to talk about the arithmetic gradient series and the geometric gradient series as well. And if time allows, we're going to talk about the compounding periods and payment periods are different. Then how we can solve the situation. Okay. So the first example for today is example 4-7 from our textbook. So we consider this situation where P is deposited into a savings account and 3 withdrawals are made. Of course, the diagram is not a standard form. So this implies that we might need multiple step solutions approaches. Okay. So first, you may think the given cash flow is a series of 3 single withdrawals, F. Okay, so here we are working on example 4-7. So let's say this is the solution approach 1. So let's say option or solution number 1. So here, like I mentioned, this given cash flow can be think of as a series of 3 single withdrawals F, which means this given cash flow can be broken into 3 different parts. Okay. So the first part is given present value. Let's say this is P1. After 2 years, there is a future sum of $20. Okay, like here. Plus, let's say P2. And after 3 periods, another future sum of 30, right? Like here. Plus, let's say P3 after the 4th period, F equals 20. Okay. So in order to get this original P value, present sum of P, you need to combine all these 3 values, P1, P2, P3. Okay? So P1 plus P2 plus P3. And how do you get P1? It's going to be 20 times P given F and interest rate. So the interest rate, okay, here I forgot to include the interest rate, which is 15%. Okay, so it's going to be 15% over the next 2 periods plus 30 times P given F, 15% over next 3 periods plus 20 times P given F, same interest rate of 15 over next 4 periods, right? And from the compound interest table, from our appendix C, you can get all these three factor values, right? So those are 0.7561, 30 times 0.6575, and 20 times 0.5718. Okay. So as a result, you're going to have $46.28. Okay. And here's another way to get the solution. So let's say this is the solution, approach number 2. In that case, the given cash flow has been broken where? Okay. So in the first approach, the given cash flow has been broken into 3 different parts. And in the second approach, again, the given cash flow will be broken into 3 different parts. However, at this time, the 3 single withdrawals are converted into an equivalent future value at the end of period 4. So we have 3 different cash flows. The first one is at the end of period 2. We have future value of 20. And at the end of period 4, we have future value, let's say, is f sub 1. Second case is after period 3. We have present sum, which is 30. And at the end of period 4, we have future value of f2. And the third case is after period 4, we have present sum of 20, and this value is exactly same as F3. Okay? And if you combine all 3 of them, then it's going to be the same as this, right? 0, 1, 2, 3, 4, 20, 30, 20. And at the end of period 4, we're going to have f value down here. Okay. So basically, this f value is same as the summation of f1, f2, f3, f2, f3. So how would you get f1? f1 is 20 times f given p, 15% over 2 years. And then f sub 2 is from 30 times f given p, 15% over 1 year. And then what about f3? f3 is just 20, right? And from the Appendix C, you can get these values, factor values. This is 1.322. This is 1.150. Okay? And as a result, you're going to have $80.94. So what's next? This future value f should be converted to the present sum, which is our target value of p. Is that right? So next step is to convert this future sum of f at the end of period 4 to the equivalent present sum of p. Okay? So how do you do that? P equals this future value, which is $80.94, times p given f 15% over 4 periods, right? Again, this factor value can be obtained from the Appendix C compound interest table, and it is 0.5718. Okay, so this value would be $46.28, which is exactly same as the one from the solution approach number 1 earlier. Okay. And here's the third approach. So let's say this is the solution approach number 3. Okay. So in the third approach, all 3 deposited values are converted to a single value P1 at the end of period 1. And then this value P1 is converted again to the present value of P at the end of period 0. Okay? So if you redraw the diagram, then what you are going to do is two, 3, and 4, 20, 30, and 20, right? And let's say at the end of period 1, we have a present sum, which is P sub 1. Okay? So let's try to get this P sub 1 value first. So like I said, is all 3 values, deposited values, will be converted to a single value of P1 at the end of period 1. Okay? So P1 is 20 times P given F, 15% over period 1, plus 30 times P given F, 15% over period 2, plus 20 times P given F, 15% over period 3, right? And all these vector values can be obtained from the compound interest table. So let's try to get those values since I don't have with me. Okay, so we are looking for 15%. So we need to look at our text page 615. P given F is given in the second column. We need to look for 3 values for n equals 1, 2, and 3. So those are 0.8696, 0.7561, 0.6575. Okay. So let me try to get this value using XR spreadsheet. So it's 20 times 0.8696, 30 times 0.7561, and 20 times 0.6575. Okay. So this value is $53 and 23 cents almost. Okay. Now what you need to do is you need to convert this P1 to the original P value, right? At the end of period 0. So now what you're going to do is we're going to have P at the end of period 0 given P1 value. At the end of period 1. Okay. So here P equals P1 times P given F 15% over period 1, right? So P1 is 53.23, P given F 15% over period 1. And this factor value is 0.8696. So again, we're going to have the final value of $46.28. Okay. So this solution is, of course, exactly same as the ones from the previous two solution method, right? Those are 46.28. Of course, there are several different ways to solve this problem, and we're going to continue to practice that with many different exercise problems, okay, later. Okay, so, okay, here's the next slide. Okay, so there are simple relationships between the compound interest factors. First, for the basic formula relating the two single payment quantities, those are P and F, is like this. Okay, so as you can see here, compound amount factor is the reciprocal of present worst factor. Okay, here. And the capital recovery factor is the reciprocal of the present worst factor. And the compound amount factor is the reciprocal of sinking fund factor. Okay. And the uniform series present worst factor is the summation of the n interest terms of the single payment present worst factor. So for example, it's like P given A 5% over 3 period would be the summation of P given F 5% over next 1 period plus P given F 5% over next 2 period plus P given F 5% over next 3 periods. Okay? And the uniform series compound amount factor is 1 plus the summation of n-1 interest terms of the single payment compound amount factor. So just for example, here F given A, let's say 5% over next 3 periods would be 1 plus F given P 5% over 1 period, F given P 5% over next 2 period, plus F given P 5% over next 3 periods. Okay? And the uniform series capital recovery factor equals the uniform series sinking fund factor plus the interest rate I. And just as an example, A given P, let's say 5% over next 3 periods is equal to A given F, 5% over 3 periods plus the same interest rate, which is 0.05, 5%. Okay? Okay, now let's talk about arithmetic gradient series, which describes a uniformly increasing series. Okay? And it may be used for the calculation of operation and maintenance costs and people's salary packages as well. And in order to discuss arithmetic gradient series, we use a notation that the capital G represents a fixed amount increment or decrement per time period. So suppose you are running a small electronic shops, and you are expecting that the revenue is $4,000 for the first year, and the revenue is increasing by $1,000 each year thereafter. Then how do you draw the cash flow diagram for this situation? So in this case, the arithmetic gradient is the $1,000 per year change in cash flows, right? So starting from 0, 1, 2, 3, 4, and 5. So for the first year, the revenue was 4,000. Second year, 5,000. Third year, 6,000. Fourth year, 7,000. Fifth year is 8,000, right? So in that case, the arithmetic gradient is 4,000 and what is the value of G in this case? This case is going to be 1,000, right? Oh, well, what did I do? Okay. Oh, I'm sorry. So in this case, the uniform annual series amount, which is A, would be 4,000, and the arithmetic gradient would be 1,000. So this diagram can be redrawn like this way using this notation: 0, 1, 2, 3, 4, and 5. So here we have uniform annual series of 4,000, right? Those are the A's. And then the arithmetic gradient is 1,000. So here we have 1G, there is 2G, 3G, and 4G, right? So if I redraw this diagram, it's going to be 0, 1, 2, 3, 4, and 5. At the end of year 1, we have the uniform annual series amount, which is A, 4,000. At the end of period 2, we have A plus G, right? A plus G. At the end of year 3, we have A plus 2G. At the end of year 4, A plus 3G. Then at the end of year 5, we have A plus 4G. Okay? So in this case, in this cash flow, we can also break it. We can also split this cash flow diagram in these two different ways. Okay. So it's going to be like one for the uniform annual series plus arithmetic gradient for n different periods. 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, and 5. Okay. So the first case is for the uniform annual series of 4,000 plus the arithmetic gradient. So it starts from period 2, 1G, and this is 2G, 3G, and 4G. Okay. So this original cash flow diagram can be broken into these two different cash flows, right? One for the uniform series, another for the arithmetic gradient. And here, one very important thing to tell you is here we have 5 periods, arithmetic gradient, right? 5 period arithmetic gradient has only 4 periods. Positive cash flow. So in general, if there are n period arithmetic gradient, it only contains 4 period positive cash flows. Okay. So here, for the first period, the arithmetic gradient 0 cash flow is added to the uniform series cash flow of 4,000. And in the second period, the total cash flow is the arithmetic gradient of 1,000 plus uniform series of 4,000. which is 5,000, right? Up here. Likewise, in the third period, it's going to be 2 times G, which is 1,000, plus 4,000. That's why we're going to have 6,000 up here. So is that the one? Okay, let's go back to this cash flow diagram for the arithmetic gradient because it's somehow very important. So if you look at the arithmetic gradient carefully, they have cash flow of 0 at the end of the first period. And the first non-zero cash flow, occurs at the end of period 2. Okay? And the arithmetic gradient of the third period has the 2 non-zero cash flow, and the arithmetic gradient of fourth period has 3 non-zero cash flows, and so on. So, in general, what I can say is n period arithmetic gradient has n minus 1, not n, n minus 1 non-zero cash flows. And this change by the amount G here. Okay? Amount G per each period. We may also say that the first period's cash flow defines the uniform annual series, and the period by period change defines the arithmetic gradient series. So while considering the arithmetic gradient here, the common mistake is to visualize an arithmetic gradient series as the n-1 periods long. The arithmetic gradient series is n periods long. Okay? But the first period has 0 cash flows. Okay? So let me just write down, because this is very important. A common mistake. In the arithmetic gradient series as n minus 1 periods long. Right? The common mistake is to visualize the arithmetic gradient series as n minus 1 periods long. Okay? Actually, it is n periods. Okay? Of course, the first period has zero cash flow. Okay? Like this. Okay? The arithmetic gradient series always have zero cash flow for the first period. Okay? So if we go back to our example, both the arithmetic gradient and the uniform annual series have a length of 5 periods here, 0 to 5. While the arithmetic gradient has only 4 non-zero cash flows, though. Okay? So this is very important. So I want you to keep in mind this. Okay? And here's the arithmetic gradient present worth formula and arithmetic gradient uniform series formula. And let's take example 4-9. Andrew has purchased a new car. He wishes to set aside enough money in a bank account to pay the maintenance for the first 5 years. It has been estimated that the maintenance cost of a car is as follows. Assume the maintenance cost occurs at the end of each year and that the bank pays 5% interest. How much should Andrew deposit in the bank right now? So let's draw the cash flow diagram based on this cash flow table. Okay? So here maybe let's use this. There are 5 periods. 0, 1, 2, 3, 4, 5. Okay? And at the end of year 1, there is positive cash flow of 120. At the end of year 2, 150. At the end of year 3, 180. End of year 4, 210. End of year 5, 240. Okay? So this cash flow can be broken into 2 different parts. One for the uniform series, uniform annual series, and another for an arithmetic gradient series, right? So 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, and 5. Okay. So for the uniform annual series, we have $120, right? And for the arithmetic gradient series, we have, starting from period 2, we have 30, 60, 90, and 120. Okay? Remember, for the very first period, there is no positive cash flows in the arithmetic gradient series, right? So we want to get the p-value, present sum, at the end of year 0, right? And let's say this is P1 and P2. Then P would be summation of P1 and P2. Okay? So P1 can be obtained by 120 times P given A, 5% over the next 5 periods, plus P2 is 30 times P given G, 5% over how many periods? Again, 5 periods, not the 4 periods. Okay? So you gotta be careful. So now let's get the table values for those two factors. So we are looking for 5%. So you need to look at our text page 608. P given A over 5 periods is 4.329. 329 plus 30 times P given G is 8.237. 237. And you will end up with $766 in such case. Okay? And this is the example 4-9. Next, let's take the example 4-11. So demand for a new product will decline as competitors enter the market. If interest is 10%, what is an equivalent uniform value? So if you look at the period by period change amount here, how much is that? It's going to be negative $6,000, right? So we may use the concept of arithmetic gradient series here. So first, if you draw the cash flow diagram based on this cash flow table, how does it look like? It's going to be $24,000 at the end of period 1, $18,000 at the end of period 2, and $12,000 at the end of period 3, and $6,000 at the end of period 4. like this, right? So instead, in that case, we can use the concept of arithmetic gradient series here. So here, if you take out $25,000 annually, what is left over? So first, we're going to take out $24,000. One, two, three, four, 0. Then what is left over? Zero, 1, 2, 3, 4. If you take out $24,000 annually, then you have 6K in negative cash flow and 12K and 18K. Is that right? Now this is a uniform series, uniform annual series, and this is an arithmetic gradient series. Does that make sense? So how do you get the equivalent uniform values, which is A would be 24,000, right? 24,000 minus, because these are the negative cash flow, right? Minus 6,000 times A given G, right? 10% over how many periods? 3? No, it's 4, right? So how much is that? From the table value, it's going to be 1.381. So this is going to be $15,714. So the projected equivalent uniform value is $15,714 per year. Okay. So this is the answer. Okay, then let's take one more example. This is example 4-12 from our text. A car's warranty is 3 years. Upon expiration, annual maintenance starts at $150 and then climbs $25 per year until the car is sold at the end of year 7. Use a 10% interest rate and find the present worth of these expenses. So again, if you look at the period by period change amount, how much is that? It's negative $25. So again, we may use the concept of arithmetic gradient series here. So like we did earlier in the previous example, if you take out $150 annually, what is left over? So if you take out $150 annually, So let me redraw this diagram down here first. So starting from 4, 5, 6, 7, we have negative cash flow of 150, 175, 200, and 225. Okay. So here we want to take out $150 annually. So here 4, 5, 6, 7, $150 each. Then what is left over? 4, 5, 6, and 7. Here, at the end of period 5, we have negative cash flow of 25 and 50 and 75 at the end of period 7. And there is no positive cash flow at the end of period 4, right? So obviously this is the uniform annual series. And this is the arithmetic gradient series. Okay. So here, if we introduce p prime, let's say right here, p prime at the end of period 3, okay, instead of p0 at the end of period 0. So if we introduce p prime right here, and let's say here we introduce p sub 1, and at the end of period 3 here, let's say p sub 2 down here. Then this p prime is the summation of p1 plus p2. Is that right? So here, this p prime can be obtained by P1, which is 150 times P given A, and 10% over the next 4 periods, right? Plus P2, which is 25 times A given, is P given G, and 10% over the next 4 periods, right? 3 to 7, which is 4 periods. And this factor value is 3.17, and this factor value is 4.378. Is that right? So we have $584.95 as the P prime value at the end of period 3. Okay, this is not the P value at the end of period 0. So next, what you need to do is convert this P prime to the equivalent present sum of P at the end of period 0. Okay? So now what you need to do is you're going to convert P prime at the end of year 3 to equivalent present sum of P at the end of period 0. Okay? So it's going to be P equals P prime times P given F 10% over 3 periods, right? And P prime is this value, right? $584.95. What is this vector value? Is 0.7513 from our textbook, Appendix C, compound interest vector tables. So as a result, you're going to have $439.47. Okay, so this is the answer for example 4-12. Okay. Okay, so I'm going to stop here for today. And next time, we are going to talk about the geometric gradient series. And then we're going to solve some end of chapter 4 problems. Okay? Okay, thank you. See you later. Bye-bye.